Okay, so we're about to move on to the next material in our construction series. But before I jump into lecture 7, I wanted to mention a few things. The first one is an apology for last week. I believe you guys are owed new lectures every year. I just think that's good practice. I think that's a responsibility I have. It shows that I'm incorporating the feedback you have, which I do try to do, and I try to advance each lecture each year. Try to either add more examples or clarify it, or kind of create it into a better PDF that's embedded into the slideshow. That said, in past years, there was always at least something that caused a lecture to be lost. There was the year I had to go to Germany, the year I had to go to Helsinki, the 2 years I had babies, the year my husband got hit by a car and had a pulmonary embolism, the year I got scarlet fever, because who gets that besides the people in Little Women and the Velveteen Rabbit? Um, all that, the time the train I was on had a pedestrian fatality. All of that to say, there's always been a lecture lost. Last week made us ensure that we don't lose any material time. And I just think that's even more important than the risk of you guys. Like, I think you guys not missing a lecture takes precedence over recording one every week. So last week should be the only time that happened. So my kids both had a gastro issue on top of all the other stuff that's been going on. And then also I wanted to apologize for Monday having to cancel, coming in to meet with all of you that are in studio. That was the worst, because I was really excited to come in and actually meet all of you. We finally had a get together with people on Saturday night. It was fantastic. We actually had friends, and the next day their 8-year-old tested positive, meaning we were in the sweet spot for exposure. Again, technically all you're supposed to do is kind of watch for symptoms, except for people who are unvaccinated. And as you all know, I have a 3-year-old who cannot get vaccinated because he's only 3, meaning he had to isolate. And if he has to isolate, I have no options. So I couldn't get a babysitter because no one could be around him, meaning I had to cancel my day downtown with you guys. That said, I'm working hard with Sam to reschedule a different day that I can come in and meet with all of you. And you still have your second round of meeting with industry professionals. So you're not going to go without talking to a structural engineer about your projects, but hopefully we'll get to have 2 conversations, one with me and one with another professional in the industry. The third thing I wanted to mention is your projects. So your projects are posted in the project module on Quercus. You have in there the project outline, and it's broken into 2 parts. The majority of you were in my course last term, so you kind of understand how this works. The first part this year, what you have to do is create a set of structural drawings for your comprehensive project. For those of you that aren't in comprehensive, there is some guidance in there of what to do. If you need more in-depth instruction, feel free to reach out to me. You're going to have to create a set of structural drawings. Make sure you talk about what your lateral load resisting system is and show where it is. And then you're going to want to do sizing guidelines use your sizing guidelines for all of the members in your project. This is supposed to be a schematic design set. And so as the architect, you would only have sizing guidelines on hand for that. And even if you retained an engineer, they would probably only do a schematic design set using sizing guidelines at that point too. The second part of the project, you have all been assigned members that you are responsible for figuring out the load, the internal loads on them. You don't have to do method of sections this time. Remember, you know the handy, quick ways to do it. The same thing we're doing in this course this term. You don't have to go back and use method of sections. You do have to figure out the loads, you have to figure out the internal loads on the element, and then you have to find the capacity of those members. And what you are going to have to do is use the big complicated formula. I also want you to check it against the tables, specifically because I want you to see that it can be done both ways. Why do I make you do the big, long, complicated formula when you can look it up in the tables? Because I have to. That is one of the mandates set out in the big wide world of what to do for this course. I know it's exactly what they make them do in all of the other major architectural universities across Canada. So I'm not just being a big old meanie, it's what you have to do for us to maintain our accreditation. That said, you're probably never going to have to do that again, ever. But look it up in the tables. You have a nice way to see if you're right there. There is a funny thing about the shear calculation for a few of the members. You guys are going to see you're going to get a slightly different answer, assuming you've done the calculations properly. For those of you that have that, reach out to me, or I might go find the old email that I sent last year and just remind people of that. I'm gonna create that note for myself right now. Send shear project announcement. It's mostly that I've told you to do something in a simple way, and the actual tables that calculate it use the complicated way. So I don't want you to have to go further than that, but that's the one thing that you might see doesn't match perfectly. Okay, so this week we are jumping into wood design. Now you guys know how to design steel columns and steel beams. You know how to make sure all of those internal factored loads are greater than the reduced capacity of the member, and how to make sure that they meet all of the serviceability criteria that's required. We're now going to go on and do the exact same thing for wood design. Now, in some ways, this lecture is a little bit easier because the principles behind what we're going to do are identical to steel. The equations look a tiny little bit different, but only a little bit. What you had was a lot of really smart people over here developing the steel equation, and a bunch of really smart people over here developing the wood equation. So they look slightly different, but they're pretty much the same fundamental process. So why do I need a whole lecture to do columns and then a whole lecture to do beams if we understand the principle from 2 weeks ago and 3 weeks ago? Well, it's because wood is slightly more complicated. The material. Steel was isotropic. Isotropic means it behaves the same in every direction. If we took a cube of steel, if we squashed it this way, it behaved the same as if we squashed it this way, which was the same as if we squashed it this way. Wood, not so much. It is different in all of the directions, and we're going to talk about that in a minute. And wood is an organic material. Steel, we make in a laboratory. Yeah, I know it's a messy, big, kind of hot, intense, crazy laboratory, but they have actual chemists there testing the steel, making sure it's perfect. Wood, somebody goes out with a chainsaw and chops it down in the woods, comes back, runs it through a machine, drops it off on a pallet in Home Depot, and you go pick one out. If you've ever bought wood at Home Depot, you know that every member looks slightly different. So, how do we build that into our design equation? And what we do is we try to simplify it. We actually have factors that allow us to deal with all of these things. So, I've talked about the project. We're going to talk about wood. I'm going to remind you of basic wood construction. What are these members that we're going to use? Then I'm going to talk about the wood factors. What impacts our design of wood that makes it different from steel? The process is identical to steel, but we're going to have to add in some factors that deal with some problems with wood. Then we're going to look at our compression design, and then I've completed 3 wood compression design examples for you. So you have 3 in this lecture, and then you do 2 in the assignment, meaning in preparation for the exam, you're going to have 5 worked out examples. You also can look up a few other things. The first one's the American code. So don't you can use it to kind of help get your head around some things, but the load factors are going to be different. Woodworks has some more examples of designing with wood in their material on their website. So you can take a look at that if you'd like to look at a few more examples. All right, so let's just remind ourselves of wood. Most of this you probably did. My 5-year-old is talking about hardwood versus softwood right now in school. So this is something that goes way back for most of you as a learning topic. Sorry. So hardwoods are usually deciduous trees. So those are the leafy ones that lose their leaves in the winter, or you could call it the end of the growing season. Softwoods are almost always coniferous. So those are needle, instead of leaves, they have needles, and they usually have cones. Most coniferous trees keep their leaves, which are needles, throughout the winter, giving them the name evergreens. In Canada, most lumber and wood products come from softwood. Now, poplar and aspen are getting used for LVL and PSL, but we're not going to design those right now. Once you know this process, you can, and the wood code has those formulas in there, but I'm not making you design with those. So why do we use softwoods? It's not because we can't use hardwoods. Hardwoods are fantastic. They actually have better properties. We can do more with them. They can span farther. They're stronger. But when we came into this country over the past several hundred years, we basically clear cut this country. And I don't mean all at once. We didn't deforest it completely. But almost every square inch of this country has been clear cut at some point. And what has grown back is softwoods. Some of it we're actively maintaining now, which is a good thing. We're doing better to manage our forests. There's a long way to go, but we have one of the best forestry maintenance programs in the world. Again, I agree, it could be better, but we are working actively on that. Because of that, we use softwoods, which grow fast and can be easily managed. That doesn't mean hardwoods aren't trying to also be grown. Back in the day, what they used to do for buildings is they would plant oak trees, let them grow for a couple hundred years so that they could use them for the next building. So churches and such in England, for example, would take that approach to managing their forests. They would plan long term. We're kind of a rush things process country over here in North America. So this is how we're managing it. All right, species of structural wood. There are a ton of types of woods. Most tend to be used for construction. Now, don't read too much into these labels. We're going to see another page, which is the ones I really want you to get your head around. So out of 30 common softwoods in Canada, 4 tend to be what we use in construction. Spruce is our dimensional lumber. So that's our 2x4, 2x6, 2x8, 2x10, 2x12, 4x4. Those are used for residential and light framing. Pine tends to be common for trim work. Cedar we use for decks and exterior applications. Douglas fir tends to be used for heavy construction, or what you're used to calling glulam. Douglas fir tends to be predominantly used in that. We then, I'm going to add this to a wood properties chart I uploaded for you. Add other wood property. Actually, I'm going to pause this for just a second and come right back to you. Okay, so how do we group these pieces of wood? So you can imagine if there are 30 different softwoods that we can design with, keeping track of that is a big number. It still gets a little bit difficult because remember, I've already said wood is different in each direction, and now we've got 30 different types of wood that we commonly design with. So what they've done is they've broken them into sections of common types of wood. It's still a lot to work with, but it's a little bit better. We have 4 different common groupings of wood. The first one is DFL, or Douglas fir larch. We have hem fir, spruce pine fir, or SPF, and northern species. So you'll often see nor or north. SPF is the most common, the spruce pine fir. If you go into Home Depot and buy a 2x4, it's probably SPF. Unless you're building a deck and you're building it out of cedar. If so, it's a northern species. So cedar lumps into this category. Most other stuff lumps into this. Hemlock, the only thing I've really designed with hemlock has been a dock. It behaves really well in a water situation, although I do know a couple architects working with hemlock right now. They're getting it directly from a mill, and they're doing it on some really cool interior spaces. The Douglas fir tends to be used in glulam. Now, we're going to jump around with these a little bit because the process is the same that I'm about to show you. But for the most part, SPF is the most popular. Probably 95% of the construction material we use is going to be SPF. All right, if you look at a cross section of a tree, the outer bit is the bark. So it's kind of the protection of the tree, and that's kind of the dry, crusty stuff. But you get inside and you have what would be called the inner bark. You don't have to memorize this. This isn't going to be part of a test, but it does help you understand what's going on with trees and why we have these factors that I'm going to show you about in a little bit. So summerwood tends to be really so springwood tends to be really fast growth, and summerwood, the tree kind of slows down, and then it stops growing in the fall and winter. That ends up with very distinct rings in a tree. Now, most of you have heard that you can count the age of a tree by its rings, and that is truth. You can see a full year of growth quite easily on the interior of a tree. The interior stuff, or the heartwood, is the older growth, and this exterior growth is the sapwood. Well, it's called the sapwood because that's where the sap flows, bringing the energy from the ground up to the leaves and vice versa. So that's how it transfers things throughout its system. Now, inside a tree, you can often get these funny little bits happening inside them, so checks and rays. What we also get, and it's not shown here, is a branch growing out of a tree. So you can imagine you have these rings like this and these rings like this trying to meet together. And that can cause weird problems within our designs as well. So here's just a close-up of the cell structure. Again, this isn't about testing you. This is about talking about the behavior of the tree. So imagine a series of straws that you've bundled together. They're going to be really great for trying to resist a squashing load. You can imagine that they're going to be really strong, less so trying to squash them with this way. Imagine taking a bunch of straws and doing that. So their behavior is going to be different in each direction. You can see here the spring growth. The cells are really, really large. They've got they grew very, very fast. And then the summerwood in its growth, they're very, very tight until all of a sudden the growth stops and then it jumps into the next spring growth. So those are just some things to think about. In a few slides, I will talk about the factors that we use to design with wood. Before we jump into that, I just want to remind you what the heck is available with wood? What materials are we using? What things are we talking about? So, nominal or dimensional lumber, and this was a slide that I showed you guys last term. I know some of you in the advanced placement didn't have the benefit of that. So this is just hopefully a refresher for you. The idea is that you should have a grasp of most of this. So our 2x4s, 2x6s, 2x8s, 2x10s, 2x12s, and 4x4s are not full size. A 2x4 is not 2 inches by 4 inches. It's 1.5 inches by 3.5 inches. Or if we were talking metric, 38 millimeters by 89 millimeters. So yes, we will convert back and forth a little bit because in Canada, a lot of residential drawings still show up in imperial. I know we're a metric company, but that is a carryover that hasn't made its full change yet. And so 2x10 is 1.5 inches by 9.25 inches. We use these for joists and studs, so that would tend to be your 2x4s, 2x6s for studs, a 2x8, 2x10, maybe even a 2x12 as joists. We use them for built-up beams. So a built-up beam is where you take multiple plies of one of these things and screw them together. So a 2-ply 2x8 would be 2 of these screwed together. When we're doing beams in wood, we always have at least 2 members. We would always screw at least 2 members together. So joists, no problem. We'll have one all by itself. But if we're talking about beams, we would always put 2 members together. Posts are a 4x4, or built-up posts would be multiple elements screwed together. So a built-up 2-ply 2x4 might be 2 of these 2x4s together. You can get full-sized lumber. It's a little bit harder to find. You tend to have to go directly to the mill, and it's not smooth like you're used to seeing from the wood. It's still rough. What they're doing is they plane that off, and that's how they get these dimensions. I built a different dock recently and got full-size lumber directly from a mill north of Kingston. Plywood is that thing that is going on top of our joists or on the outside of our studs. Typically, we're talking about 1/2 inch or 3/4 inch. We're not spending a lot of time on this. This is more just a refresher. Eye joists, we're not really going to get into designing these, but these would take the place of joists. Our PSL or LVL, they're engineered lumbers. We're not going to be doing anything with these right now, but I just wanted to remind you they exist. Last term, we talked about using these with sizing guidelines. And then we can have mass timber construction with glulam elements. And then everybody's favorite wood star right now is CLT, or cross-laminated timber. Now again, this was just a quick refresher to remind you of these different types of woods. Mostly right now, we're going to be designing with nominal lumber. So that means the 2x4s to the 2x12s and 4x4s, maybe even a 6x6 thrown in there. Because that's, the process is the same for the other types, and I need to go through one of them in detail. If we do all of them, I don't have time to do any of them in detail, so I prefer to teach you one rather comprehensively. So what could make wood harder to design than steel? Well, it has moisture in it. We go cut down a tree and that sap oozes out of it. It shrinks. So even once it's dry, it tends to shrink somewhat. That's all of those long, skinny cells in it kind of shriveling up. It's non-isotropic. Remember, isotropic means it's the same in every direction. Non-isotropic means it's different in the different directions. And so those same thing, those long, skinny cells, squashing them this way is different from squashing them this way. It's imperfect. So we can have knots in our tree. So where a branch comes into the side of the trunk of the tree, we can have a flaw in our material there. Those checks and rays that we saw in the cross-section of the wood, those can cause flaws in our piece of lumber. It creeps. So that means if we put a load on it for a long time, it will deform separate from our elastic deformation. So that means we have our elastic deformation, and then it'll creep a little bit more. If you take the load off, the elastic deformation will return back to normal, but the creep won't. You can end up with permanent deformation that has nothing to do with yielding. So don't confuse those two things. We're not going to do much with it, but we are going to build in factors for these things. Wood rots, or it gets eaten by bugs if you put it in the right environments, and wood burns. So what can we do in our design to account for all of these things? Remember, with steel, our steel columns, we knew that if it was really short, it would squash. If it was really tall, it would buckle. If it was somewhere in between, it was some combination of squashing and buckling. So wood is the exact same. We have those exact same problems that we have to deal with. But now we also have to deal with these problems. So here's what we do. We create factors that we go through to determine the strength and the stiffness of the material we're designing with. So the first thing we have to do is figure out what type of wood we're using. Then we have size factors. The size factor is about determining what the odds there are of a flaw being inside our material. There's system effects. How are they behaving relative to each other? Load duration. This is about that creep factor. Service conditions. So this is it wet or dry, which means will it rot? Chemical preservation. So that is also about trying to treat it from moisture or fire retardant. And then we have the one factor that we worried about with steel, which is lateral stability or buckling. Out of all of this list, we know all of this for steel. It was just 350 MPa steel. That was easy peasy. We didn't have to worry about more than that. And then we had to worry about buckling. Well, for wood, we have all of these factors that we have to add into it. Okay, this is just, I'm not testing you on this. This is just a nice refresher. Wood construction almost has its own lexicon or its own way people talk about things. So remember, in steel, our purlins were the thing that occurred regularly. Well, in wood construction, we call those joists. So they're just a basic piece of wood that occur regularly and tend to support the plywood. But then we get into like funky things like jack posts and king posts. A particular beam over a window is a lintel or a header. We'll have double plates on the top, sill plates on the bottom. A trimmer goes around a stair. All of this to stay. A stringer is a beam that supports a stair. All of these to say mostly we're talking about beams and columns, essentially. A joist is just a type of beam. A post is just a type of column. A stud is just a type of column. So we have compression elements and we have bending elements. And this is just fancy names for all of those things. All right, when we are designing with wood, we usually look at our sizing guidelines, come up with a size for something, and then we're going to design it to see if it works. When we do that, we have to know something about the material. And so we'll often start with an assumption about the material or the grade of the material. I'm going to tell you that construction and standard are not ones we're going to use. Those ones are graded by a machine. So what's grading? So literally what they do is they send all of these pieces of wood down a conveyor belt and somebody stands there and says, great, good, bad, horrible, amazing. And they sort them based on that. Amazing is called select structural. Very good is number wood. Pretty good is number 1. Pretty good is number 2. Okay is number 3. And is stud. So they visually grade these pieces of lumber. You can have a machine grade, but we tend not to use those. Those tend to be kind of mass-produced, churned out things like planking. And you can get it for light framing, but if you go to Home Depot, you will see a symbol. Most of the material you see in Home Depot is going to say SPF number 1, number 2. And so SPF is spruce pine fir, number 1, number 2. It's been visually graded as being very good to pretty good. Not amazing, not okay, and certainly not ugh, but somewhere in the middle. Okay, so that is the majority of the lumber we build with. And then we have to know, what job is it doing? And its job has something to do with its makeup as well. So often we can figure out what grade category we need to define it as based on its size and its grade. So these things we're picking. We're just throwing a dart and picking these things. Now, it's not so much throwing a dart and picking these. We're probably getting this from a sizing guideline, so we have a place to start. And this is about knowing what we want to use. Select structural, while also being stronger, looks the best because visually it had the least flaws. So if you have something exposed architecturally, you're probably going to want to pick select structural. If it's just a regular old bit of construction, you're probably going to use number 1, number 2. Sometimes for studs, we might do number 3 or stud. Often I usually specify number 1, number 2 for 95% of my projects. With knowing this, we can figure out what grade category we have. Now, why do we need to know the grade category? Well, the grade category tells us what properties our material has. So these all have different load tables or property tables that are assigned to it. So here's our very first one, table 6.3.1a. Specified strengths and modulus of elasticity for structural joist and plank, structural light framing, and stud grade categories of lumber. So if we were any of those things on this table, so stud, structural light framing, or structural joists and planks, we could use this table. Now look at this. Douglas fir, hem fir, spruce pine fir, or SPF, northern, which would be cedar. And then here we have our grade, select structural, number 1, number 2, number 1, number 3. Look at this. Bending at extreme fiber. Well, bending at extreme fiber means here and here. They're talking about FY. Now, wood is brittle, so we don't have FY. This does not yield. So we care very much about what happens at this and this point in bending. If we start to fail here and here, the whole thing's done. It is a brittle failure. So the extreme fibers, remember in a rectangle, we did that whole derivation of what happened to the stress profile. Well, if we hit that maximum load, if our extreme fibers exceed this stress, we got a problem. It's not going to work. Anything below this, we good. We're all right. We don't care if we are less than this. We care if we go over this. So if we're going to determine something, we might as well talk about it right at that limit. But look at this. We have not just FB, we have compression parallel to the grain. Well, remember all of those tubes, or those straws, if you wanted, those cell tubes? Well, imagine those are all running up the tree. And now we're going to cut it into pieces of wood and we're going to squash it. Our load is acting parallel to those tubes. Load perpendicular to grain is if we're trying to squash those tubes. Most of the time for columns, we're going to be talking about compression parallel to the grain. And then look at this, longitudinal shear. So that is a shear trying to transfer along our plane here. So we have 3 different categories for our strength or our maximum stress we want to see, broken out into different grades, broken out into different species. For steel, we just had 350, maybe 345 if it was a hot rolled section. And that was the limit of it. We had one number we needed to worry about, whether it was in compression, whether it was in bending, or whether it was in shear. Already we have all of these. But wait, there's more. We have other grade categories. This was just our first table. Don't worry about this one. We're not going to use table B. These are the ones for that are machine graded. Let's go to the next one. This is the one for beam and stringer grades. Look, we've got all of our species identifications, our grades, and then we have all of our different maximum stresses we can see. And then we have table D, which is for post and timber grades. So we went from having one grade for steel to having, God, how many? 3, 6, 9, 12, 24, 28 times 3. So, almost 90 different strength possibilities for our wood. They also list here modulus of elasticity. So we have E and E05. Don't worry about this. This is just talking about the 95th percentile of something occurring. Basically, if we were talking about distribution and we bound it, we're going to cut out a portion of these values. So basically, we build in a reduction to our modulus of elasticity. So imagine that there was another load factor that we already built in. Depending on whether we're talking about strength or compression, we use one of these two things. So it'll be very clear when we look at the equations which one of these we need to pull out to do our work. So that's our strength and modulus of elasticity. That's a lot of information, but we haven't even talked about our factors yet. We have more that we have to do here. So we would go figure out what our strength is, but then we need to modify it based on its specific condition. So that's what they go cut down in the woods that we can go buy at the store. But then what are we doing with this thing? That can have an impact on how we treat the strength as well. So the first one is the load duration factor. The load duration factor says, well, this is basically accounting for creep. If something is sitting on this for a really, really, really long time, it can cause some creep on it, which can reduce its strength capacity. If it's a short-term load, like a really fast load, we actually get to say it's stronger than we typically would. Now, standard term is, you guessed it, gonna be standard. I think I have one question on the assignment where you wouldn't use standard term. Everything else we do is gonna be standard term. So unless you hear otherwise, always use 1 for KD. Just use 1. If you hear somebody say short term or long term, yeah, then come look at this table. But you would very distinctly have those trigger words from me. You would hear me write or say short term or long term. So standard term means the condition of loading where the duration of specified loads exceeds that of short-term loading but is less than long-term loading. Yeah, what a obvious statement. Examples include snow load, live loads due to... Oh, Jesus. We have the kids' bath toys are in a basket that is attached to the side of the shower with a suction cup, and it just came crashing down. I'm in the house for the first time by myself in forever, so that really caught me off guard. I apologize. That startled me. Jiminy Cricket. Okay. So, snow loads, live loads due to occupancy, wheel loads, and dead loads when they're combined with something else. So if a dead load is combined with these, and which is most of the time. One of the interesting ones is wind. Wind and earthquake are considered short-term loads, but most of the time for wood construction, we're talking about live load and snow load. And so we'll see that. System factor. Okay, this one, for whatever reason, always screws people up, that if it's not part of a system, people try to use 0. Don't do that. If it's not part of a system, its factor is 1. What this says is if it's part of a system, we can say that it's stronger than we think. So what does being part of a system mean? Essentially, if we have things close together that have the potential to share the load any one object is getting the benefit of the things adjacent to it. So imagine you're building a deck and you don't have the top of the deck on, but you have all of your joists on it, and you stand in the middle of one of those joists. All of your load is going to go on that one joist, right? Well, what if you get off and then you put the decking across all of the joists? And now you go back and you stand directly in the same spot. You're over one particular joist. All of your weight is on one joist, except you're standing on top of the decking. If your weight pushes that joist down, it pulls the deck along with it. And for the deck to go down, it has to try to bring the joists beside it down just a tiny little bit. Meaning, by activating the middle joist, you're engaging the joists on either side of it by the fact that it's got the deck on it. And that is what accounts for a system. If it's a post, if it's a beam, it's not part of a system and its factor is 1. If it's a joist or a stud, it's probably part of a system. So those are your trigger words right there. Joist, stud, you can be pretty certain it's going to be part of a system. If it's a beam or a post, you can be pretty sure it's not going to be part of a system. Now, there are very specific clauses of when it's case 1 and case 2. I'm going to tell you that most of the stuff we do is going to be case 2. A normal house, which is a normal thing, would be case 2. So just the way they build things. So they say here, joists and rafters sheathed with plywood, a minimum of 9.5, with panel coverings. Basically a normal floor construction. If we've got that, you can assume case 2. So I will try to be if you see me say, kind of a normal building, you will know I'm saying case 2. So if you see stud or joist and normal construction, you will know it's a case 2 system factor. So look at this, system factor. Case 1, we're not really going to use that much unless I explicitly say to you it's case 1. Case 2, here are our system factors. All right, what's the next one? Service condition factor. If it's dry, it's 1. No big deal. If it is a wet service condition, it has some dimension limits here to tell you what KS is. So if it's outside, it's wet. The underside of a joist or the underside of a deck construction, we tend to consider it wet because the water runs down through the deck or splashes up from the underside. I go back and forth sometimes on a soffit of a roof. I would always start with wet and reduce its capacity, and then maybe if I'm pushed, and I would talk to the architect about what the finishes are. Interesting side note, a pool roof is a wet service condition. The humidity is so high to keep a pool heated, it would be considered a wet environment, and we would need to use the wet service condition. Oh, but look at this. So they have KS for bending at extreme fiber, KS for shear, KS for compression parallel to the grain, which remember is the one we're going to be doing most of the time. But there's also KS for the modulus of elasticity. We actually have to keep track of how it impacts the stiffness of the member as well. Treatment factor. If it is untreated lumber, it's got a treatment factor of 1. So that just means your regular old lumber. Preservative treated incised lumber. Unincised lumber. Service condition or a treatment factor of 1 for dry or wet. Preservative treated incised lumber, thickness of 89 millimeters or less. So what does that mean? What they're saying here is pressure treated. If we have pressure treated lumber that's unincised, it doesn't impact its strength. So what does incised mean? So I'm going to draw, let me get my big fat pen here. Oh, I don't want to use that one. Okay, so I'm going to fold this piece of paper and I'm going to show you what I mean. So pressure treating is something we do when we have wood outside. So this protects it from being wet. So this helps protect the wet or rot factor. Remember, if we looked at service conditions, well, we would still reduce it, but we help try to prevent rot by putting a treatment on it. So let's take a look here. If I have these two pieces of wood, what we do to try to protect them is pressure treating. We put them in basically a liquid solution, and then we put it under extreme pressure, and it seeps into the perimeter of the member. So if you've ever cut pressure treat lumber, it tends to have like a color variation that looks like this. The outside is treated and the inside isn't. If you make a cut, we often buy kind of a seal coat or end coat where you just brush it on the end to add some pressure or some preservative to that end cut of our piece of lumber. Incised lumber, they basically go around with, think of it as like a dimple maker for pasta or something like that. It basically punches little holes in the lumber. So it would punch little holes in the lumber like that. So when it goes in the pressure treating bath, our pressure treatment goes a lot further into the lumber. I have never seen a 2x4 or a 2x6 that's been incised ever. 2x8s, it seems to be whoever is the supplier. I've bought 2x8s, pressure treat 2x8s that are incised, and I've bought ones that aren't. 2x10s and 2x12s pressure treated are almost always incised. And you can tend to see them, it looks like they have staple marks all along the outside of them. Fire retardant treated lumber, there's a special clause here for that. I can tell you I have never done fire retardant on my lumber. I know Dave has been doing it for a lot of the mass timber projects they're working on now, but it would be a special class of building to be doing that. Size factor. So the size factor, you would think that the smaller the lumber, the more you would reduce its size factor, or the more you'd reduce its strength. It's counterintuitive. It's the exact opposite. The size factor tells us that, you remember where we had the trunk and the branch coming in? Well, if we're cutting a small piece of lumber, remember we're grading these with our eyes. We look at the outside of it. We can't see what's happening inside. A small piece of lumber probably shows all of its flaws on the outside. If there's a knot inside of it, there's probably a portion of it that you can see on the outside. As our piece of lumber gets bigger and bigger and bigger, the odds of there being a flaw hidden inside it actually increase. So if you have a member this big and a knot this big, you'd see it. It would be pretty obvious and it would be graded accordingly. If you have a member this big with a knot this big, it could be hiding right in the middle of the lumber and you not know. So as the size increases, we actually reduce the capacity. For small members, we're so confident that the flaws have been taken into account that if you've got a really good looking piece of lumber with no flaws on it, we say, you know what, we're actually going to bump up the strength on that. And so that's what our size factor is. Interestingly enough, for built-up sections, we get to use the size factor for individual members. So if we had these same two pieces of lumber, this would reduce its strength because it's one big thing and the knot could be hidden in here. But 4 pieces of wood screwed together one big knot would be visible, and it already would have been accounted for in the fact that it was select structural versus number 1, number 2 versus number 3 versus stud. So built up sections, we can use the actual individual member size to determine our size factor. All right, compression design. This equation doesn't look so bad. It's not scary. It's not as ugly as our steel one, right? We have our reduction factor here. Sorry. We have our reduction factor of 0.9 for wood in compression. Capital FC. All right, well, they've given us an equation for this, a small fc with a bunch of our factors. Well, small fc is the specified strength or stress in compression parallel to the grain. That's from those first tables we looked at, whether it was table A, C, or D. Remember, was it joists? Was it light steel structural framing? Was it post and timber? Was it beams? That tells us which FC we need. And then we multiply it by our factors, KD, KH, KSC, and KT. So our duration, system, service condition, and treatment factors. We then multiply it by our area. So we know area, we can calculate that. So B times D for a rectangular section. KZC is our size factor. Let's go back to this for a second. So this was our size factor. Look here, for bending and shear, they gave us all the values here. For tension parallel to the grain, they gave us one, but we're not really doing that. We said that the one we're going to worry about the most is compression parallel to grain. If we're talking about a column, all of our tubes are running in this direction and our load is going to be parallel to the grain. Well, value computed using formula in clause 6.5.6.2.3. Well, I can tell you that that is this equation right here. And it is 6.3 times D times LD or B times LB to the power of minus 0.13. At most, we can increase our strength by 30%, or our size factor has to be less than 1.3. So if we get 1.7, too bad. We don't get to increase it that much. We use 1.3. It might reduce the strength. Why are there two different things to think about? Well, this has to do with what direction we could be looking at. So it's a size factor based on its our width to our length and our depth to our length. Okay, then we have KC. KC is our lambda. Do you remember lambda? Look at this equation. This is the equation for KC. This looks very similar to our lambda equation. Remember, it was 1 plus a bunch of stuff. Well, this is messy looking. Don't worry about it. Let's break it down. 1, easy enough. Capital FC, we've already figured it out. KZC, no problem. We figured it out right here. That's our size factor. CC cubed. We don't know that one yet. Let's park that one for a second. Divided by 35 times EO5. I told you that was something we look up on the charts where we look up our strength. KSE is our service condition, but for our modulus of elasticity. And KT is our treatment factor. So no problem. The only thing we don't have here is CC. CC is our buckling length ratio. So what we're saying here, in steel, a steel element was usually freestanding. We tend to have them locally and they're braced at each floor height. So if we squashed it, it was pretty obvious that it was going to try to buckle in its weak axis. Remember, we were very worried about IYY for buckling, but IXX for strength, or for for bending, for stiffness, for deformation. Well, remember I showed you what happens if we just put our finger here. It changes our unbraced length to that dimension. Well, wood is interestingly often embedded within other things. We often have plywood attached to it. So what we're saying here is we don't know what direction it's going to try to buckle. So we have to think about both directions. And LB is our effective length associated with each direction. So in this version, the unbraced length is the same for trying to buckle it in that direction or try to buckle it in that direction. And you can tell at a glance that LB and B are going to govern it. But look at this. If I brace it here, well, we now know that its unbraced length is this in the strong direction, but half of that for the short direction. So it's probably still pretty obvious which way it's going to go. What if I said this was in between something and it couldn't buckle at all in the weak axis? Well, we don't know when it'll try to buckle in that direction, but that's the direction it could try to buckle because it can't buckle in the weak axis. It might be governed by strength, but it might be governed by buckling in its strong direction. So we have to think about now its strength, buckling in the weak axis or buckling in the strong axis. And so this tells us which one to use. And then we would use the appropriate size factor in that equation. So basically we're going to track two things. Sometimes it's going to be obvious right away which one governs and we don't even need to bother with it. But most of the time we're going to track both things. And it'll be obvious as we start to look at some of these. Okay, let's look at the two different equations that we did for steel and wood. So for wood, it's PR, which is just another way of saying compression resistance. Why did they pick a different one? Meh, who knows? The people doing the wood code weren't talking to the people doing the steel code, so they used different symbols for things. The important thing is that they are very similar equations. It doesn't look like it, but look at this. They both have their reduction factor. They both have their cross-sectional area. They both have the maximum stress we want to see in it for compression. For steel, it happens to be Fy because it's isotropic. But for wood, it's the compression parallel to the grain. We've built in some factors into this. And then we have KZC, which is just another factor, and KC, which is our buckling. Well, KC, remember, was 1 plus a bunch of stuff to the power of a -1. So KC is very similar to this portion. Really, what we're saying for both of them is we have a reduction factor, we have the maximum stress we want to see, we have our cross-sectional area, and then we have some factors for the material and for buckling. They are essentially the same equation. They just look a little bit different. So we're going to follow the same process that I always talk about, where we look at everything we know and see if we can solve each individual element of the equation before we go plug everything into it. So don't get overwhelmed by the big overall equation. Stop and look at each individual thing within the equation, get as much information as you can, and then go back and try to solve it. So let's look at how this plots out for a given element. Remember for our steel column, when it was really short, it was governed completely by squashing. And when it was really tall, it was governed completely by buckling, to the point that if it was tall enough, we said, we don't even care how much capacity it has. We're going to say we won't even let ourselves load it in that condition. And then in between those two extremes, it was some combination of squashing and buckling. Well, it's the exact same thing for wood. Look at this. Here is our compressive resistance for squashing. Here is our compressive resistance for buckling. And then here is the final compressive resistance. So for this element, I solved all of those things using the elements within this equation. So for squashing, I basically did this. For buckling, I looked at this. And then for that final red line, I actually calculated out the full PR. So here you go. Here's the compression resistance for the depending on its unbraced length for a wood column. And this looks very similar to our steel one. So this is where really, as much as those equations looked slightly different, you can see they're doing the exact same thing. And look, we have an upper limit here as well, that after this height, we don't care. We won't let it have capacity anymore. All right, now the fun part. Now we get to do some examples. Okay, the fun stuff. All right, the very first example we're gonna do is to determine the capacity of an 89 by 89 wood post. That's a 4x4. So remember, 4 inches by 4 inches is actually 3.5 inches by 3.5 inches. So we've got ourselves an 89 by 89 wood post. It's 2.5 meters long in an interior environment. So we can deduce some things from that, but we'll get to that in a minute. The wood is SPF number 2 untreated. So they're going into the store and they know they're just gonna buy SPF because that's the most normal thing, especially inside a house. And it's untreated because why would you treat it? It's inside a house. We normally do that for outdoor conditions. Okay, so we want to figure out what the capacity of this member is. So let's make this big. All right, so we want PR of, let's see if I can get this a little, oh, I won't go any closer. PR of 89 by 89 post. It's 200 or 2,500 millimeters tall. Dry, untreated, and SPF number 2. Okay, let's start writing out what we know. I tend to break it up into a few different components here. So what we know. Wood. Let's figure out what we know about the wood. Well, we know right away that the reduction factor for wood in compression is 0.8. So we've got that one. That one we know. We got that in a formula. Grading. We don't know what the grading is. We have to figure that out. So let's come down here. Let's go back. Let's go back to that table that had the grading in it. Okay. We want to know what grade category we are. Here are the different grades. So we know that we have number 2 lumber. So it can't be this, it can't be this. So it could be any of these. So we could come over here. It's in this category here. The smaller dimension. Well, the smaller dimension is 89 millimeters. So it could be either of these two categories. It's under 114, so it's not these ones. So it's gotta be one of these two things. The larger dimension was only 89 millimeters. It was square. So it can't be this. It looks like our grade category is structural light framing. So I'm just gonna write that in here. So structural light framing. Well, with structural light framing, we know we can get a bunch of information from a table. We just don't know what table. All right, we have structural light framing. Oh, look at this. structural light framing. We get to use table 6.3.1a. Well, we were told that we have SPF lumber, and it was a number 2. Okay, we know we're talking about something in compression parallel to the grain. So it looks like we can come over here and we can get a bit of information. We are going to have a specified strength of 11.5 MPa. If our column has more stress than 11.5 MPa, our column isn't going to work. Now, we know there's a few things we can do with that, but 11.5. We also know that for columns, we may need our EO5 or 6,500 MPa. So we have a few more things that we can write in here. So we got that our FC was 11.5 MPa and our E05 was 6,500 MPa. So we've got a few things going for us here now. We've got a few things we've calculated. Okay, now we have to worry about our wood factors. Now, remember in our equation, maybe we should write out our equation. Let's go back to that equation. Let's take a look at it. We know that we're gonna wanna figure out all of these factors. So let's go back up and start figuring them out. Too far. Okay, well, the first one, so these are our factors. KD. Well, they didn't tell us what loads were on it, but it said it was a pretty normal house. And remember I said, unless I told you something pretty specific, we're gonna be standard term. So standard term, KD, is 1. That's nice and easy. All right, system factor. This said it was a post. When did I say right off the bat? You know what, I'm even gonna add this to slide 23. Post beam. I'm just gonna put a little note there for you guys just to really lock it in. So if it's a post, it's not part of a system because it's not sharing that load out with anything. So if it isn't part of a system, its KH is 1. All right, let's go to our next factor. Service condition factor. We know there was a few things that we could look at here, and we're talking about compression parallel to the grain, and we know we have a modulus of elasticity that we've pulled, so maybe we should get these two, so KSC and KSE. So KSC and KSE. Let's see. Well, it said it was inside. To me, inside means it's dry. It's going to be protected from the elements. It's going to have an envelope around it. So everything is a factor of 1 if it's dry. So 1 and 1. Okay. Treatment factor. It said it was untreated. So untreated lumber always has a KT of 1. Size factor. Well, for compression parallel to the grain, we need to use our formula. We don't get to use the table. Looks like we'll get to use the table next week when we talk about bending and shear. But this week, we're going to have to use the clause to figure it out. All right. So we figured out all of our factors that we could looking at those tables. So let's write out what we know about the member. We know its depth is 89 millimeters and its width is 89 millimeters. Which one's depth and which one's width would really only matter here based on its unbraced length, because we have a length in one direction and a length in the other direction. I mean, it's the same length. The whole element is 2.5 meters tall, but this is talking about where it's braced. Now, this is a post out somewhere in the building. We don't know if it's in a wall or not. Because we don't know what it's doing, we're going to say this thing is unbraced. So its full length is, its unbraced length is its full height. So we have everything we can figure out from the question. We have to start solving some problems here. We know that the equation for a column, PR equals our reduction factor times our capital FC times A times KZC times KC. Well, we have our reduction factor. That's the only thing we have so far. So it looks like we have a few more things we have to solve here. So that one we've got, we have to figure out what capital FC is. Well, capital FC is lowercase fc times KD times KH times KSC times KT. Well, we already know what lowercase fc is. We looked that up here. It's 11.5. KD is 1, KH is 1, KSC is 1, and KT is 1. So it's 1 times 1 times 1 times 1, or 11.5 MPa. Well, this seems kind of boring so far. Seems like we've done a lot of stuff, but haven't really done anything at all. But now we have FC. Area. Well, we know area is B times D, so we can calculate that. 89 times 89. Let's figure out that. 89 times 89 is 7,921 millimeters squared. Okay, we've got our area now. KZC. KZC is ugly. KZC is a big old ugly equation that is 1 plus capital FC. Oh, sorry. Never mind. I'm reading one step ahead here. All right. KZC isn't so bad. KZC is 6.3 DL D to the minus 0.13, or 6.3 times BLD, or BLB minus 0.13. Well, we're only going to check this once because look, D and B are the same and LD and LB are the same. Remember, this is all about its propensity to buckle in either direction. All right, so we would normally, if these dimensions varied, we would check both of these things. But for us, it's the same. It's 6.3 times 89 times 2500 to the power of 0.13. So 6.3 times 6.3 times bracket 89 times 2500 to the power of minus 0.13 equals 1.27. Now that is, in fact, less than it is less than sorry, I'm kind of half talking to myself here. Yeah, it is less than our 1.3, so we're good. We've got a KZC here. Now, KC is, big bracket, 1 plus capital FC KZC CC cubed, I always forget that cubed, Try to remind me, yell at me. I'm going to forget that cubed. 35 EO5 KSE KT end bracket to the minus 1. Okay, well, capital FC we've already calculated, KZC we've calculated, EO5 we've pulled from a chart, KSE we looked from a chart, and KT. So the only thing we don't have is CC. All right, so CC is either LD divided by D or LB divided by B. Okay, well, it looks like these are the same. LD and LB are identical, and D and B are identical. So we just need to do this once. 2,500 divided by 89. If you're wondering, what do I do if these are different? Don't worry, we're going to do another example that looks at that. I won't leave you high and dry on that. So 2,500 divided by 89, we get 28.09. That looks like it filled out everything for KC for us. Now we can calculate KC. KC equals 1 plus our FC we've calculated as 11.5 times KZC we calculated as 1.27, that's our size factor, times our CC cubed is 28.09 cubed over 35 times our EO5. Our EO5 we looked up is 6,500 times our service condition factor for stiffness, but it's 1, times our treatment factor, which is also 1. And then end bracket minus 1. So let's plug this into our calculator. Okay. We have 1 plus 11.5 times 1.27 times 28.09 cubed divided by 35 times 6,500 times 1 times 1, end bracket, end bracket, end bracket, to the power of minus 1. And we get KC of 0.4127. Remember, this is our buckling factor. So this is telling us that it's not, if this was 1, it's not governed by buckling. If this was almost 0, it's entirely governed by buckling. But this looks like it's somewhere part strength, part buckling. Okay? So now we have our KZC and our KC. It looks like we can calculate PR. PR equals our reduction factor, which is 0.8, times our capital FC, which was 11.5, times our area, which was 7,921 millimeters squared, times our KZC, which was 1.27, times our buckling factor, which is 0.4127. All right, let's calculate this. We have 0.8 times 11.5 times 7,921 times 1.27 times 0.4127 equals 38,195 newtons. We find it a pain in the ass to talk about newtons once we're talking about the actual forces. So we're going to talk about it in kilonewtons now. It was useful to use newtons and millimeters for our calculation, but now we're going to say it's 38.2 kilonewtons. So whatever load is on that column has to be less than 38.2 kilonewtons. We now know the capacity of an 89 by 89 post, or colloquially a 4x4 post, an SPF number 2 4x4 post. That happens to be 2.5 meters tall inside a building. We don't know if this particular one works or not because we don't know what the load on it is. Now, I am not completely evil, so I have also given you load charts. So there are compression tables that I have provided for you. Let's open this up here first. Oh, where did that go? You little stinker. Here we are. We have posts here, and that it talked about being on sorry, let me get my bearings here. Oh, it doesn't. Okay, well, so let's go find that in the charts then. All right. So this is sawn lumber. Oh, look at this. Post 89 by 89. The length where KE is 1. So basically that's talking about what does it look like when it's deformed. And we're saying that usually we've just got a normal old column that's got a floor above it and a floor below it that's kind of bracing it. Okay, so where our length is 2.5 meters, and we have SPF number 1 or number, so 2.5, we come across SPF number 1, number 2, 38.2. That's exactly what we just calculated. So it looks like we did something right here. Go team. Okay, so here it is in that chart. Let's do another example. Let's do an example. A column sees a PF of 105 kilonewtons. Does 140 by 191 cedar select structural 4.5 millimeters tall work. Assume inside untreated. So this is one where we're going to look at two different bracing elements. So assume inside and untreated. If not, brace the weak axis halfway up. Does it help? Okay, let's take a look at what we know here. All right. PF equals 105 kilonewtons. We have a 140 by 191 cedar, select structural, 4,500 millimeters tall. It's inside, untreated, and unbraced. Inside, untreated, and unbraced. B, same as above, but weak axis. Braced halfway. All right, let's figure out what we know. All right, let's start with the wood. Well, we know that the reduction factor for compression is 0.8. We want to figure out what the grading is. All right, let's go take a look at our tables, shall we? I'll get us up there. Here we go. We have to figure out our grading. Okay, let's take a look. Our smaller dimension is 140. So this isn't it, this isn't it, this isn't it, this isn't it. So it looks like it's one of these two. Now you probably have a guess which one, but let's just follow the rules and see what it says. We are 140, so we're 114 or more. The larger dimension is 191. So there's a difference there of 51 millimeters. Okay, exceeds smaller dimension by more than 51, exceeds smaller dimension by 51 or less. Well, we're exactly 51. All right, and we were told we're using select structural. So it looks like we do fit this category. We get to use the table that talks about post and timber. So let's look at that. Post and timber looks like it's table D. So 6.3.1D for specified strengths and modulus of elasticity. They told us it was cedar. So cedar is a northern species. It was select structural. They gave us this in the equation. And we need to know what the compression parallel to grain is. It looks like it's 7.5 MPa. And EO5, which we know we need to help calculate our buckling, is 5,500 MPa. So 7.5 and 5,500. All right. So it is post and timber. We have a lowercase fc of 7.5 MPa and EO5 of 6,500 MPa. It was 6,500, right? No, it wasn't 5,500. 5,500 MPa. 5,500 MPa. Okay. Now we know we have to think about those factors. All right, let's think about factors. All right, KD. It didn't tell us it was anything unusual, so I think we're pretty safe to assume it's a standard term load factor. System factor. Again, this is a post. It doesn't say anything about it being part of a system, so that doesn't seem like something we get to mess with. So we're going to have a system factor, or sorry, KH of 1. It's not part of a system. Service condition factor. So KS for compression and KS for modulus of elasticity. So KS for compression, well, we were told it was a dry service condition, so it looks like both of these are 1. The last one is KT. Well, KT, they said it was untreated, so it looks like KT is also 1. So that was the end of our, oh, no, we have one more. KZ. Well, KZ for compression parallel to the grain involves a formula. So we don't know yet. We don't have something we can just write down. So it looks like we'll have to calculate that when we get to it. Okay, let's see what we know about the member. All right, let's calculate what we can about the member now. We know we have our depth is 191. Depth is just always usually the bigger one. Don't worry about it too much. B is 140. Our LD is 4,500. And LB is 4,500. Except in the second question, they do tell us to do something different. So if this doesn't work, they give us a modification to make on this number. So we'll just park that for right now. Okay, so let's figure out what this is. Let's write out our equation here. Let's remind ourselves of our equation. Actually, maybe let's just start calculating things. Let's figure it out here. All right, area equals 191 by 140. Area is 191 by 140, or 26,740 millimeters squared. All right. Capital FC is lowercase fc times KD times KH times KSC times KT. Well, we have 7.5 times 1 times 1 times 1 times 1, or 7.5 MPa. Let's right away calculate our CCD and our CCB. Well, they're not the same. Remember last time they were the same? This time they are not the same. So we are going to track both of these. So for CCD, it is 191 divided by 4,500. And for CCB, it is 140 divided by 4,500. But we don't know what the difference here means. So what we're going to do is we're going to continue to track both directions of failure here. Sorry. I wrote those backwards. Don't mind me. So 4,500 divided by 191 and 4,500 divided by 140. 4,500 divided by 191 is 23.56, and 4,500 divided by 140 is 32.14. We don't know what the heck that means. That doesn't really give us any information. So now let's calculate our KZC. So KZC, let's calculate it for D, and KZC for B. Remember, it's 6.3 times 191 divided by 4,500. And that is to the power of minus 0.13. And we have 6.3 times 140 divided by 4,500 to the power of minus 0.13. So right now we're just tracking both of these things because we don't know which direction is going to govern. Now, you probably have a good guess. If the length is the same for both of these, do you think it's going to buckle in the weak axis or the strong axis? Yeah, my guess is the weak axis is going to be what buckles here. Okay, so 6.3 times 191 divided by 4,500 to the power of minus 0.13 is, I am not plugging things in strongly into my calculator today, am I? 6.3 times 191 divided by 4,500 to the power of minus 0.13. Oh, guys, I am totally sorry. I don't know what I'm doing here today. I am just totally, oh my God, I did it again. I divided when I should be multiplying. I am really so sorry about what my brain is doing today. Oh, okay. Those are big multiplications, not divisions. I don't know. Luckily, I know that the answers don't look right because I know that these should be somewhere around 1. 6.3 times 191 times 4,500 to the power of minus 0.13. All right, 1.0663. All right, and then let's do the same thing, but instead of 191, we have 140. 1.1103. Okay. Now we have to figure out our buckling factor. So this was our size factor. We have to figure out our buckling factor in both directions. So this one's the messy one, remember? So here we have 1 plus our FC, our capital FC is 7.5 times our KZC, and so this one's for D, so it's 1.0663, times our CC cubed, and this is for D, so 23.56 cubed, divided by, why am I doing this in such a messy way? This is really annoying to you guys and to me. All right, KCD, that was, I didn't like that, sorry. So 1 plus 7.5 times 1.0663 times 23.56 cubed, I always forget that cubed, divided by 35 times our EO5, which is 5,500, times our KSE, which is 1, times our treatment factor KT, which is 1, and all of this is to the minus 1. All right, we need to calculate this for KCB as well, right? We're checking it in both directions, just to be thorough. We're pretty sure it's going to buckle in the weak axis, but we're tracking both of them just in case. So now we have 7.5 times 1.1103 times 32.14 cubed divided by 35 times 5,500 times 1 to the minus 1 equals. Okay, let's plug this big messy thing into our calculator. All right, bracket 1 plus bracket 7.5 times 1.0663 times 23.56 cubed, and bracket divided by bracket 35 times 50 times 5,500. I'm not even going to put those ones in. And all the brackets to the power of minus 1. All right, we get a buckling factor of 0.648 for, how many cricket? 0.648 for the strong axis. Let's calculate this for the weak axis now. I am a mess here today, folks. All right, 1 plus 7.5 times 1.1103 times 32.14 cubed divided by 35 times 5,500 to the power of minus 1. We get a buckling factor of 0.410. 5. Let's bring that over another dimension here. Okay, so we are able to calculate our actual capacity now. So PR in D and PR in B. So this, remember, this is about what direction it buckles in, and we don't know which one is going to fail first. Remember, some side is going to cause it to fail first. All right, so our overall calculation for CR is our reduction factor, which is 0.8, times our FC, our capital FC, which is 7.5, times our area, which we calculated is 2,740, times our size factor, which is 1.0663, times our buckling factor, which is 0.6480. And then in our weak axis, our reduction factor is the same, our strength's the same, our area is the same, our size factor is different, and our slenderness factor is different, or our buckling factor. So let's take a look at what our PR is. So see, it's not obvious. This is lower, but this is higher. So it's worth calculating both. Times 7.5 times 26740 times 1.0663 times 0.648. We get, I'm going to divide it, this is in newtons, I'm going to divide it by 1,000 right now to get it in kilonewtons. We get 110.9 kilonewtons. Down here, 0.8 times 7.5 times 26,740 times 1.1103 times 0.4105. And we're going to divide it by 1,000 right away to get it in kilonewtons. 73.1 kilonewtons. So remember, we need to know if this column works for a PF of 105. Well, in its strong axis, it works, but in its weak axis, it doesn't. And both axes are valid at the same time. So this does not work. PR equals 73.1 is not greater than PF equals 105 kilonewtons. Does not work. So I like to be very bold and clear that I checked this thing and it didn't work. Now, they said if it didn't work, they had a feeling this might be the case, but let's brace that axis halfway up. So for our strong axes, everything stays the same. Nothing changes in our strong axes. We've already calculated it, so that we've already got. We want to figure out what PRB is if we change it up a little bit. So for PRB, or our capacity in the weak axis for tendency to buckle, B still equals 140 millimeters. But LB, it said we're going to brace it halfway up. So we've got a shorter unbraced length now. So what happens if we've got an unbraced length? Well, our size factor changes. So we can calculate, well, actually a few things change. Our CCB changes, our KZCB changes, and our KCB changes, which means our PRB changes. I know, that was a lot. I know it sounds ridiculous when I just say all of those letters. Well, let's calculate our CCB. CCB is our LB divided by our B, or 2,500 divided by 140. We get 16.07. KZCB is 6.3 times B times LB to the minus 0.13, or 6.3 times our 140 times 2,500 to the minus 0.13. So 6.3 times 140 times 2,500 to the power of minus 0.13. We get 1.215. It is less than 1.27, or sorry, it is less than 1.3, so we're good. We can use that value. And now we can calculate our buckling factor of KCB, which is our 1 plus capital FC times our KZCB times our CCB cubed divided by 35 EO5 KSE KT all to the minus 1. So for us that is 1 plus 7.5 times our new KZC is 1.215 times our CCB cubed is 16.07 cubed divided by 35 times 5500 times 1 times 1. All of that is to the minus 1. We can plug this in and we get, all right, bracket 1 plus bracket 7.5 times 1.215 times 16.07 cubed divided by 35 times 5500 to the power of minus 1, and we get a buckling factor of 0.8358. Okay, so we've got a buckling factor now. That means we can calculate PRB, so our weak axis capacity, and we know that that is the reduction factor times capital FC times A times our size factor times our buckling factor. So we've got 0.8 times 7.5 times our area of 740 times 1.215 times 0.8358. Just squeaking it in there on the page. Or 0.8 times 7.5 times 26,740 times 1.215 times 0.8358, and we get a capacity of 162.9 kilonewton. We can divide that by 1,000. That was in newtons. So 162.9 kilonewtons. So now that's our weak axis capacity. Our strong axis capacity is still 110.9. So now PR equals 110.9. It is greater than PF equals 105 kilonewtons. Works. So we need a 140 by 190 select structural, so it was a select structural post with braced at 2.25 meters weak axes. So we actually have to do something to this to make sure it doesn't fail. We have to brace it at some height to make sure it doesn't fail. Okay, so that was 2 examples that we've gone through. You haven't done one with a system factor, but I can tell you if you come up with one that is a stud, you get to use case 2 system factor. All right, let's do another example. Oh, my tummy's growling. I apologize. Okay, does this look familiar? We've touched on it the past 2 weeks we've done work. So we're designing a steel canopy. They gave us the dimensions. They gave us the roofing assembly. They told us the location and the climatic loading. Well, Let's consider the steel canopy we designed in previous lectures. The contractor has suggested a cost savings by substituting wood members in lieu of steel. They're proposing the following. For the column, a 140 by 140 Douglas fir number 2, and for the beam, a 140 by 343 Douglas fir number 1. We don't know how to do that yet, so we'll worry about that next week. We want to assess whether the proposal is structurally adequate. Recall that this would be considered to be a wet service. It's outside. Now, luckily, we already did a bunch of work. We, in Lecture 5 and Lecture 6, figured out what CF was, what MF was, what VF was, and what our serviceability loads are. So we're good for a huge portion of the work. We now just need to figure out what PR or CR is, and then next week we'll take care of this part. Okay. So we want to know, does a 140 by 140 Douglas fir number 2 work? It's a post, and do you remember that its height was 4 meters? Now, what do you think? Is this the unbraced length? Yeah. It's a post outside. There's nothing bracing it. There's nothing connecting it anywhere that's going to stop it from buckling. So it looks like it's going to be the same in both directions. It's a 140 by 140. So it looks like it is the exact same in both directions for height and dimension, which means we really only have to go through the calculations once. We know what its setup is. Okay, and they have told us that CF equals 23.3 kilonewtons. It's wet, untreated. So we need to figure out everything we need to know about this member. All right, let's figure out what we know about wood. Well, our reduction factor for a wood column is 0.8. We know we're going to figure out what grading is. We're going to figure out what our lowercase fc is. We're going to figure out what E05 is. And then we're going to figure out all of our factors as well. All right, I'm going to lower this. Let's go look those things up. Go way back to the beginning. Okay, here's how we figure out our grading, our grade category. All right, we have a smaller dimension of 140. So that's gone, that's gone, that's gone, that's gone. So it's one of these two. Our larger dimension is also 140. So exceeds smaller dimension by 51 or less. So it looks like post and timber. We have a number 2, so that seems to work. We've got post and timber grade. So post and timber. So post and timber isn't table A. We're not using table B. It isn't table C. It looks like it is table D. Great. So table D, we can get our FC, or our compression stress parallel to grain, and our modulus of elasticity. And for columns, we like E05. Well, they told us it was Douglas fir, and it's number 2. So look at this. Wow, 7.5. It was the same one as it was. It's the same value as it happened to be. Like, none of these are, most of these are different. It just, what a coincidence that these happen to be both 7.5. And it is just that, a complete coincidence. So we've got 7.5 for a Douglas fir number 2 post, and our E is 6,000, or our E05 is 6,000 MPa. Let's take a look at our factors. Seems like KD is 1. They haven't told us that there's anything fancy going on here. It's standard. So KD is 1. All right, system, it's not part of a system, so our KH is 1. If it was a stud, it would be part of a system. So see, walls, plywoods, and studs are a wall, which is a stud with plywood on it, is a case 2. Service condition factor. Well, they did say it's outside, and we know that means it should be wet. So it's a wet service condition for sawn lumber, which is what we've got. Okay, if it's 89 millimeters or less, oh, well, we don't have that. Both of our dimensions, so this is for the least dimension, both of our dimensions are 140. So we're over 89 millimeters, and we want to know what the factor is for compression parallel to grain. It looks like our KSC is 0.91. Modulus of elasticity is 1. So there's no change in the modulus of elasticity though. What's our next factor? Treatment factor. It's a wet service condition, but they told us it was untreated. So KT is also 1. Size factor, we know for a column, KZ is a formula, so we can't really do much with that right now. And we know that we have this equation that we need to solve. So we know, we can write out some stuff about our member as well here. So let's write out some stuff about our member. So B equals 140 and D equals 140. LB equals 4,000 millimeters. Look at me not writing units. And LD also equals 4,000 millimeters. So it looks like this one's the exact same in both directions. So we don't really need to worry about directionality so much. All right, we know that PR equals our reduction factor times our capital FC times A times KZC times our KC. Well, we've calculated that. We need to figure out what FC is, which is lowercase fc times our KD times our KH times our KSC times our KT. So for us right now, that is 7.5 times 1 times 1 times 0.91 times 1. So we actually have a reduction in the maximum stress we'll let this see because it's outside. So 7.5 times 0.91 equals 6.825 MPa. So this column can take less load because it's outside. All right, our area is 140 by 140. So let's calculate that. Or 19,600 millimeters squared. KZC is the next thing we need to calculate. KZC, we know it's the same in both directions here. So we know it's 6.3 times our 140 times 4,000 to the minus 0.13. Because it's going to be the same in both directions. B and D are the same, and LB and LD are the same. So 6.3 times 140 times 4,000 to the power of minus 0.13, and we get 1 1.1274. It's less than 1.3, so we can go for it. That seems to be the right one. Okay, the next thing that we calculate is KC, but we know KC needs our CC value. And CC is either LD divided by D or LB divided by B, or 4,000 divided by 140, because it's the same in both directions for this one. So 4,000 divided by 140 gives us 28.57, which means we can calculate our KC, because KC is 1 plus our capital FC times KZC times CC cubed divided by 35 EO5 KSE KT to the minus 1. Okay, we have 1 plus 6.825, because remember, we had to reduce that lowercase fc, times our KZC, which we calculated is 1.1274, times our CC cubed, or 28.57 cubed, divided by 35 times 6,000. KSE is 1 and KT is 1. And all of that is to the minus 1. Okay, let's plug that into our calculator so we can get our buckling factor. We have 1 plus 6.825 times 1.1274 times 28.57 cubed. I haven't forgotten that yet. I'm pretty proud of myself. Screwed up a bunch of other things, but not that. Divided by 35 times 6,000 to the power of minus 1. And we get a buckling factor of 0.539. So now we can calculate what PR is. PR is 0.8 times 6.825 times 19,600 times our KZC, which is 1.1274, times our KC, or our buckling factor, 0.539. This is going to come out in newtons, so I'll divide it by 1,000 right away. 0.8 times 6.825 times 19,600 times 1.1274 times 0.539 equals, I'm going to divide it by 1,000, I said, and we get that it equals 65 kilonewtons. So we've calculated it, but they told us to make sure that it actually works. We want to see that PR equals 65 kilonewtons is greater than PF equals 23.3 kilonewtons. It works. Let's just verify that against those tables I gave you. Okay, so we did this calculation manually. Let's take a look what happens when we look at the tables here. Okay, so these are sawn lumber. Let's get to columns. So these are some bigger columns here. Sometimes I have to hunt around. Ooh, look at this. Oh no. This is Douglas fir #1 sawn timbers. So this isn't the right page. Douglas fir larch #2 sawn timbers, square timbers of 140, by 140, which is what we have, for a height of 4 meters, look at this. It calculated 68.4. We calculated 65. Did we do something wrong? No. This is assuming, if you look down here, this assumes standard term load, dry service conditions, no fire retardant. Well, we didn't have a dry service condition. We had a wet service condition. So our value ended up being just a little bit lower. So these tables are great, but as soon as we deviate from norm, they're slightly less helpful. They give us a good idea on if we're close or not. Like if we had calculated 5, not 65, we would know maybe we had done something wrong. Or if we calculated 1,000, we would have a pretty good idea we made a mistake somewhere. But we know it should be slightly less than the 68.4 that this gives us is the answer. Okay, so here it is all worked out. Maybe we could find a smaller or cheaper member. So it looks like these are the smallest member, and number 2 is what we use. Doesn't seem like we're gonna get anything smaller there. So let's just take a look at the comparison from what we did last week. There wasn't a smaller wood section available. There just wasn't a smaller one. Our steel, we calculated we had a 64 by 64 by 3.2 was the smallest section. Now, this steel was 5.82 kilograms per meter. Our 140 by 140 Douglas fir is going to be about closer to 11 kilograms per meter. Okay, these prices here, I calculated these prices very roughly about 5 years ago. What do you think has happened to these numbers right now? Yeah, absolute poppycock. In fact, for a recent period of time last year, this value more than doubled. It's about 1.5 times this right now. So this is going to work out to be more expensive per meter than this. But maybe aesthetic means this wants to be the answer. So we don't really know what one's going to be chosen. The contractor suggested this as a cost savings. Maybe that was true 5 years ago. Maybe they can get a discount, but it seems within the realm of reasonable. Maybe the architect looks at it and says, this is fantastic. There's wood columns inside the arena. We want to match the aesthetic. Let's go with the wood. So this was an option worth checking. Okay, so what did we learn today? What have we learned? All right, so wood strength depends on the wood species. So if you're doing something in cedar, it's not going to be as strong. Wood is organic and has all kinds of things that impact the strength. Wood column design includes compression buckling. Wood comes in many forms, including engineered products. Those are the main things you need to know going forward. What we're going to be talking about that you have to know to do your assignment and to do your project and to do your exam is you have to know how to choose the wood grade. Actually, you don't really need to know how to do it to do your project. Know and determine wood strength factors, how to calculate CR for columns, posts, or studs, how to look up CR for available sections, and how to identify if the column works. That just means write that nice little note that I like PR is greater than or isn't greater than PF. And so that now we have wood column solutions. So we know how to do a steel column, and now we know how to do a wood column, which means we can start to compare the relative merits of the two systems. Next week, we're going to finish our wood section by talking about our wood beams. So we're going to talk about joists and beams in wood next week. So see you next week.